Hi everybody. I thought I'd have a look at day 7 element of code um, because it's a problem which there's a simple solution to it, and it's a solution which suddenly occurred to me a couple of days ago, and I thought I'd solve this using emacs lisp because that's a fun thing to do, and because Gavin, who I will link to in the doobly-doo, already solved an element of code puzzle using emacs lisp. And he taught me a lot about emacs lisp, where he solved the problem. In that with Emacs you can perform functions on buffers. You open a file and then you can run code on the text in the file to modify it. And he manipulated the data doing this in order to make it very easy to process, which was really interesting. And someone wrote a comment on his video. Saying, well, there are these nice libraries which you can add to Emacs, which also are quite a lot of fun to use, and they make life a lot easier. So I dived in and had a look at these libraries, and I thought I'd show you some of what these libraries can do. But about the problem, this is day 7, and my first basic idea is that you have a tree structure. You have a file system. And then questions are asked about this file system. Like the first question is, so you can see here, this is the little test data. So you can, just as a small example, your puzzle input is actually quite a lot longer than this, but it has this structure. And then they show you that this test data, you can pass it and you go to a file system, which looks like this in some sort of YAML format. Then you can find the total sizes of the directory, so you add up j, d.log, dx, and k to get to the size of d directory, etc., and the size of the root directory is the size of everything added up. And then the first question you get is find all of the directories with the total size of at most 100,000, then calculate the sum of their total sizes. So in this case, that would be the directories, which other directories here are at the most 100,000 large, and then add them up. They say it's A and E. Well, maybe that would well be the case. So my first impulse when I saw this was, well, let's do this in an object-oriented style. So we're going to have an interface node with two implementations. One of it's going to be a class called directory. One of them is going to be a class called file. And we're going to pass this input and build up our graph. Each directory can have a list of nodes inside it, which can either be directories or files. Node as an interface will have a function, will have a method calculate size, which will do different things if it's just a file, etc., etc. You can imagine a solution, and one thing you could also add to each node is you could have a method accept instrumentation, whatever you want to call it, accept visitor, and the visitor would take that node itself as an argument and would then do something with the information the node provides. At which point you could build a visitor which solves this particular problem, or build a visitor which then solves problem for part 2. Heavily over-engineered as a solution. A very general, very beautiful solution, but heavily over-engineered. And yes, you could do that in Common Lisp or in Emacs Lisp, of course you could. There's the Emacs Lisp object, EIO object system, which is quite capable. But it's a lot of work. And it occurred to me that there's a much easier way to solve this, and that is you don't actually need to build up this complex tree. What you could do instead is you could have a hash table, and the key of the hash table would be a directory path, and the value would be the size of everything in that directory path. That's all you need to do. Yes. There's one more thing which you have to bear in mind, is that you have to calculate the size of the total size of everything under the directory. So with the hash table, you're going to have to, if you want to add something to directory E, you would also need to add it to directory A and add it to, so add something to key E, you'd also need to add it to key A and add it to key slash, or it wouldn't be key E, it would be key slash A slash E and key slash A and key slash. That's where you would add it. But that's quite a small problem. That's quite a small thing to pay for. To have a situation where you could just pass this input line by line, which makes life a lot easier. Okay, talked enough. Let's have a look at a possible solution. So here's my emacs. Here's the short input. Here's a dired. Let's just start a code.el and let's have a look. Okay, I'll just dive in here and write some comments about my solution. There's a nice function. There's a very nice library, which was mentioned by this person who commented on Gavin's video, called f.el, which helps to deal with files. Short.txt. So this, for example, just reads the input to the file, as you can see, which is great. And there's another very nice library called s.el, which will then allow you to pass it into lines. Because I'm not sure if there's anything at the end, let me remove any blank lines. This is also a function in s.el. No, this is a function in bash.el. So that would be the first block. Now that's quite tricky to read. Let's have a look at it, make sure we understand what it does. So f.read text inside, that reads the text from input short.txt, that which you can see on the left. S.lines breaks it into lines, so it breaks on any new line character, and you get a list coming out. And then remove will drop any items from the list which fulfill this predicate. So they fulfill, if they're blank, they will be dropped. Now this is not particularly easy to read in this form, and for this reason there are some wonderful macros which are part of Bash, and also quite a standard Lisp thing. So you can find them in Closure. These are the so-called these are called threading macros. They have nothing to do with threading, and so in concurrency and multi-threading and doing many things at once, it's a different meaning of the word here. And threading macros basically, well, let me just write it using a threading macro, and then it'll become clear. Okay, then s.lines, and then remove s blank p. There it is. Okay, and that works as well. So I think so now it's fairly clear what that does. It takes whatever the first argument is. In this case, if it's on the first line, in this case is f.read input short.txt, and inserts that as the second argument, as the last argument on this line, inserts it then and inserts the result from that as the last argument on this line. So what the macro actually produces at the end of the day, when the macro is run, when this minus greater than is run, it actually produces exactly what you see here. It's just easier to read, particularly if you've got lots and lots of things which are doing on the same data. This is easier to read. Okay, good. So that gives us all the lines. And now, because we're just going to look at this as being a hash table and not some sort of complicated tree structure, we can deal with this line by line without any difficulty. The problem with looking at it as a complicated tree structure is what do you do with these file listings? So when you look at for example, the file listings here at the end, how do you pass them line by line if you are trying to build up a complicated tree structure? This ls function will need to somehow be given these 4 lines as its response, so it can start adding things to the tree start adding things to the file system tree, etc. And that makes life very tricky, or it makes life more difficult than if you can find a way to solve this line by line. So what's the next thing we have to do? Well, let's just write a function to do this line by line. Let's save this somewhere. qlines. Let's save that. So now we have lines, and then we have lines. Let's do another function from bash is each. And let's create our own function to do this. Let's just call it process line at this moment. We don't have this function, of course, yet. Good. Why isn't each process line part of this block up here? Why do we need to save lines in between? Well, we don't need to save lines in between. We could just put this here. Oh, it gets quite tricky to understand if we do that. We could do this, but it's not particularly easy to understand now. And why we would need to do that is because, let's get this back to where it was. It's because process line, it's because each doesn't take lines here, but the lines need to go here. The definition of each is, if you see in the mini buffer, it takes the list and then the function, and not the function and then the list. The list is the first argument here. And for this thing up here, the list is always the last argument. So we can't add an each to that part. Okay, so let's have a look at this process lines function. What are those things which we could do with a line, in other words? Well, let's have a cond, because there are going to be quite a few things we can do. Let's start with some simple things, which this could be. So s equals p line could be cd dot, which just means go to root. So let's have a function cd root, which we will then write at some stage. It could be, what's the next thing which we will be looking at here? cd dot dot. So let's have a function cd dot dot, which I will write at some stage. It could be, have we got another s equals? No, we haven't. We have an s prefix. P. Yes, s prefix p. Sounds good. These are all functions in s.el, by the way. cd. So it could be we're moving to a new cd. Could be that we're moving to a new directory. At which point let's have a function cd, and let's have a substring of line starting at 1, 2, 3, 4, 5. Should be the directory name itself. We could line could start with the word dir, I suppose, with the dir directory. If it does, let's well, this means it's going to be a new directory which we haven't had before. So let's add this directory to our hash table. Let's call our hash table dirs. That's going to be 1, 2, 3, 4. We need to cut off. Yep. And the other thing it could be is just a file listing. So that's the last thing it could be. Process file line. Let's call it that, and give it line. So this is a basic thing we need to do. Let's add some stuff. Now we need a directory. Let's start with the directory. Let's just add it. There's a very nice library called ht, which I found recently, and this allows you to create hash tables in Emacs. Emacs has built-in hash tables, but the functions offered to modify the hash tables I find to be quite complicated. Functions to work with the hash tables, rather. And ht is a nice library which contains a couple of functions I find really useful. For example, you have this function ht, which allows you to create a hash table very easily, and this hash table is just give it a list of pairs here. And this case, I'm giving it the pair of the root directory. It's just 0. Let's make this a little bit clearer. We're going to need at some stage a root directory, so let's call that root. Get this. Don't need this there. Okay, that's good. What else do we need? The current directory. We're going to have to save a lot of state while passing, not just to the ht hash table, not just to the dias hash table, but we need to save state while reading the file. We need to save state of which directory we're actually in. So I'm going to have a directory called current, which saves that. Which to begin with is set to root. It doesn't need to be, of course, but it can be so. So let's start with some simple ones here. Let's start with some simple functions. Defun cd dot is quite simple. That's just set q current root. That's an easy function. Let's find a cd dot dot. This is a more complicated function. The first thing we have to do is make sure we're not yet in root, because if we are in root, we don't want to do anything. So let's make sure that we are not in root. And then what we need to do here is we need to cut something off the end of current. So current is going to look something like this. Just to make life easy, let's have current looking something like A, B, C. So we'll always put a slash on the end of current. I'll make life a little bit easier to deal with. So what we need to do here is we need to cut off not just the slash, but also everything up to the next slash. And this isn't that easy to do. What I'm going to do is going to regard it as a there are probably some quite simple emacs functions to do this. Directory manipulation. There's probably a way just to add dot dot on the end and then say to emacs, tell me what that is. But unfortunately, I don't know the functions, so I'm going to do this using using a threaded macro. I'm going to take current. I'm going to turn it into a list. I'm going to reverse it. So then I can drop something from the start, which is minus drop 1. That drops the first. And then I can drop while. Sorry, while. Not car equal. Let me explain what this one's doing, because I think this one is a little bit unusual, this line. Now, the first thing you may be wondering is why there are two slashes at the start of this line, there's two minus signs. And this is a macro inside a macro. So this here is already a macro minus greater than the greater, and this drop while is also a macro. And what this does is it allows you to use this argument, which is given, as it here. So each drop while takes a list, and each element is actually can be addressed by it here. So this means drop while from the list of things it's getting, the string's been turned to a list, if you remember. So we started with slash a slash b slash c slash, for example. We turned it around, so it's now slash c slash b slash, sorry, we turned it into a list, so kind of a list of these characters, 1 2 3 4 5 2 3 4 5 6 7 characters after each other. We reversed it. We dropped the first one to get rid of the last slash. So at the moment we're now, let's just write this. So we turned it into slash c, sorry, a slash b slash c slash, all of them individual characters. Then we turned it around, c slash b slash a slash, and then we dropped the first slash. And then we're telling it to drop while the character is not a slash. So now we're going to get into that. It's going to be after this drop while line, at which point we just need to reverse it and turn it back into a string. So reverse and concat. And that's the whole function. But it's quite a nasty function for this fairly simple task. But that's the simple way to do a CD dot dot. You see, it's a way which I found to do it. I imagine there's an easier way to do this, but I don't know it. Good. Okay. So what's the next thing to do? cd dir is the next thing to do. cd change to a new directory. So define cd a new directory. So this is what's being called here. So we're going to get something like an A or an E or something. For example, dir E here. I'm sorry. Yes, no, not that. It's this one up here, isn't it? So we're going to get something like an A or something like a D here. This is where we are now. So we're going to be modifying current. So set q current. What do we need here? We need to have concat current dir, and then let's add a slash on the end, which is define cd. That works okay. What's the next thing we need to do? Add dir to dirs. Let's do that one. We haven't done that yet. Define add dir to dirs, the directory. So, this is an ht function, isn't it? The first time we're using the hash table functions. Apart from the ht function to create the hash table, and they're using ht_set to set something inside the hash table. And ht_set works by, first of all, you need the name of the table, which is dirs in our case. And then you need the name of the key, which is what? Well, it's going to be concat current dir. That again, that's the name of the directory, and we're going to give it the starting size of 0 because there's nothing in it. Okay, that sounds pretty good. Then we need the process file line function, which is something we haven't yet written. This is going to be a little bit more complicated. Let's see. Fun process file line. So this is when we, in our ls output, we get a file. That's what am I doing? That sounds better. So what do we need to begin with? We need to get the size of it, which is that's just the first. We can split this on the space and then take the first one, which is well, first we need to get the parts, don't we? Which is s split. Or s words would be even better, wouldn't it? S words line, and then we take the first one, which is just string to number. First item parts. That should do it, I think. Does that look okay? Yes, I think that's okay. So now we have the size, and now we need to, for each element, for everything in HT, we have to check if we should add this size to it. Because if you think about it, something I said earlier, everything is in the root directory. So the size of the root directory gets added to no matter where you put a file in the file system. And inside directory A, there's also a directory, I think there was a directory inside A, wasn't there? Yeah, CDA, and there's directory E. So anything you add to directory E will also be added to the directory A, for example. So the way to do this is a hash table. The HT library gives us an HT each, which allows us to work through the file. So this gives, it takes a function, which is a k and a v. It takes a function which is given as parameters the key and the value. And then at some stage we're going to have dirs, which is what it works on. So ht each takes a function, strangely, in the mini buffer you can't see it very well describe what it does. So let's see if we can find it here. Ht each. Apply function to each key value pair of table. Okay, makes sense. Nope. That's better. Good. Okay. So the function is what we've got to write here. if s prefix p. So where we can find if a directory should be added to. So if you add something to a directory a/b/c, then the size should also be added to directory AB and directory A. So anything which is a substring, which is a prefix of the directory, of the current directory, should have this size added to it. So if s prefix p, k current, so if k is a parent directory of the current directory, then we add the size, and let's set this as well. So ht set dears k plus v size. Okay, this is okay. ht set, what's the order? Table key value. Yeah, that makes sense. Cool. Okay, let's get rid of this. We got this right. I think that's a little bit better. Yeah, ht.dears, this looks a lot better. Okay, good. So this is, we're now getting pretty close to an answer. Yep, we've now gone through the file processing stuff. Let's see if this works. Let's get it to spit out dears at the end. Message dears. Ooh, dears. And let's eval buffer. So if I can avoid s words, it's not s words, is it? I thought it existed as words. Words. No, it doesn't. Okay, then s split. Like that. Okay, I thought there was an s words. Okay, not important. Eval buffer. Symbols avoid parts. Okay. What am I doing wrong now? Split blah line. Parts. Okay. Of course, we need a star here, don't we? Looks better. Eval buffer. Add dear to, what have I done now? Add dear to dears with a minus. Okay. Eval buffer. We've got stuff. Cool. We printed the message buffer, didn't we? So let's go there and see what we're doing here. Okay, we've got stuff. It looks okay. 48361165254. Okay, these buffers are wrong, aren't they? Current dear, cd dear. What am I doing wrong there? My new buffers are totally wrong. CD, substring line 5. Looks okay. Set Q current. Tell me what's going wrong here. Okay. Ooh, something's gone wrong here. Because I'm doing a CD slash. There's a space here, isn't there? This is where things are going wrong. Okay. Good. Let's try this again. Yes, that now looks better. Okay, are these also the right answers? Let's see. So AE is 584. Let's look at A is 94853, and according to them, A is 94853. Okay, cool. So what we need to do, find all the issues with the total size of at most 100,000. Okay, so now we just need to write a couple of list comprehensions, to go through HT, which is quite simple, really. So let's just try this. Sum of files under 100,000. Okay, so we go through dirs. There's a very nice function called ht.values as part of ht, which gives you the values of the key value pairs in the hash table. I'm not sure they're sorted, so let's make sure we can sort them from the bash library. That would sort everything ascending. And we take while it is less than 100,000, and then we sum it, and that's it. And we get to nothing because sum is in the bash library and starts with a minus. Okay. And we get to 95437 here. And the solution which they have for the test data set is 95437. Okay. And just to make sure it works, let's try this on the large data set, which I already saved here as input. And we get, as you can see, it's a lot longer, a lot more data, and the hash table is very large, much larger. We get that 1513699, which is what I got the first time. Good. Okay, cool. So I don't think we need this here. Let's get rid of this. What other messages do we have here? That's something else we're passing out. Let's get rid of that. So let's look at the second half. The second half. Now you're ready to choose to delete. The total disk space available to the file system is 7 million or what? It looks like 70 million. Yes, it's 70 million. To run the update, you need unused space of at least 30 million. You need to find a directory you can delete that will free up enough space to run the update. In the example above, the total space size of the outermost directory and thus the total amount of used space is 48 million. This means that the size of the unused space must currently be that, which isn't quite the 30 million we'll quite be able to do. Therefore, the update still requires a directory with a total size of at least 8 million to be deleted before it can be run. To delete this, choose the following options. E, A, D, and root. E and A are too small, D will not be big enough, whether it is D and root are both big enough. Between these, choose the smallest, D, increasing unused space by 249. Okay, find the smallest directory that, if deleted, would free up enough space on the file system to run the update. Okay, so basically what we're going to do is we're going to take the values, we're going to sort by size, we're going to drop while they're too small, and then we just take the first item, basically. So what is the size we need to find? Space to free. Let's think about this. We have 70 megabytes total size on the disk. We need to have at least 30 megabytes free. Total amount of space is, well, what is the total amount of space? Let's see what it is. ht get dirs. That's something I'd like to see. F.el buffer. Message it. Sorry. Root size. That should do it. F.el buffer. ht get, is it not ht get? Oh, I need to put this in brackets, don't I? F.el buffer. And root size is 46 million gerade at the moment. So we need to free 6 million. So how do we work out? Well, it's root minus 40 million, isn't it? That's what we need to free. So let's call that here. Let's write that down. Q space to free s minus ht get dirs. And it's 40, 123, 123. Okay, there we are. And let's
message smallest dir to delete, and let's also have another comprehension. D would be better than S. Well, I wrote S up here and it worked fine. Whatever. Okay. Dirs. So for each dirs, we're going to get the values. We're going to sort again in growing in ascending order, because we want to drop while they're not big enough. Less than it space 2 3, and then we just want to take the first. So first item. Okay, and let's run this. Eval buffer. And the smallest directory to delete is 7991939. I don't know what directory it is, because I just discarded the keys by using ht values here, but who cares? It's the answer which is important. 7991939, and that's what we got here as well. Cool. And yeah, this library, this bash library, is really quite fun when you can write stuff like this. It's quite easy to read, I find. It says take directories, which is a hash table, get the values from the hash table, sort, drop while it's too small, and take the first item. There's maybe one other thing I'd like to talk about here in this solution. There's something which I don't like particularly, and that's this block here, process file line. I think there's a lot of low-level stuff going on here, in that we are walking through our hash table. Let's get rid of these comments up here. We're walking through our hash table and doing stuff on a number of directories. And it would be nice if there was an ht function, there's a function in the ht library, something like ht mutate or something. Unfortunately, this function doesn't exist, but you could imagine a function, something like ht mutate. So define ht mutate, which takes a hash table and a function. And what this then does is it runs an ht each with a function which takes k and v, and then sets table k on fun call of fkv for table. You can imagine something like this, which will then it takes two arguments, the directory, the table, so the dirs in our case itself, and a function which will be run on each key value pair, and then it updates the value as a result of this function, which I think's quite a nice way of looking at this. I think it'd be quite nice to add that to the ht library. Maybe I will ask if that's possible. Okay, cool. Well, I hope this was interesting to some people. Hope this, I will get this pushed to YouTube. Talk to you all soon. Bye.